to gravity. I've come across the question quite a lot. Why do planets manage to float in space? What keeps them up there? Well, the answer is absolutely nothing. They're falling. Everything in the universe almost is falling. The Earth is falling towards the Sun. The Moon is falling towards the Earth. The International Space Station is falling towards the Earth. The Sun is falling towards a giant black hole at the centre of our galaxy. Everything is falling. So how come, if we're falling, why doesn't anything hit? Why doesn't the Earth crash into the Sun? Why doesn't the International Space Station fall to the ground and crash into the ground? And why doesn't the Moon crash into us? Well, what's going on is that it's moving around the Earth at a speed that's so fast that it doesn't crash into the Earth. In the same way, the Earth is moving around the Sun at a speed that's so fast it doesn't actually crash in. And when something is always falling and never hitting, we call that an orbit. This concept was first invented by this handsome fella here, Sir Isaac Newton, and he came up with this equation: force equals the universal gravitational constant times the mass of the attracting body times the mass of the falling body, all divided by the distance between them, centre to centre distance between them, all squared. And this, he said, was so serious. Back in those days the word for serious was grave. He said this was a matter of the utmost gravity. And that is what we're going to look at today. Gravity. Okay, so how do we keep something in this perpetual state of always falling but never landing? Let me just clear some space and we will look into that. Okay then, so we've seen that force is of gravity is equal to the universal gravitational constant times the mass of the attracting body times the mass of the falling body, all divided by the centre to centre distance between them squared. But Newton had something else to say about force as well. He said force, and you might be familiar with this one, is equal to mass times acceleration. So if we wanted to know how fast something was accelerating, then the acceleration under gravity, which we might prefer to call g rather than a, is equal to the mass times the acceleration, which we're going to call g, but we can get rid of that. So the force is equal to mass times acceleration, which is equal to, the force is equal to gm, and the little m, which is the accelerating body, divided by the distance between them squared. We note we've got the little m here and the little m here, which cancel out, which confirms what our friend Galileo said, that the mass of the falling object is irrelevant. So the acceleration under gravity, g, is actually equal to Newton's gravitational constant times the mass of the attracting body, all divided by the distance between them squared. So if we take this equation, we can know how much a body is being attracted to the ground. But we want to know how fast we can throw a body across the surface of the attracting body, in this case maybe the Earth. How fast could we throw, say, the International Space Station across the Earth so fast that it can be ever falling and never hitting? Well, there's another law in physics, which you may have experienced if you're on a bus and it goes round a corner, you get thrown to one side of the bus. You might have also seen this in your spin dryer as it throws the water out of your clothes. And this is called centripetal acceleration. This is the amount a body has to be accelerated towards the centre of a curve or an arc or a circle in order for it not to fly off in a straight line. And that is given by the acceleration is equal to the speed squared divided by the radius of the arc. And you might have seen it demonstrated if someone puts a bucket of water and they throw it over their heads, but the water doesn't actually fall out onto their heads because they swing it so fast the water never comes out. What's keeping that water from falling on your head is this concept here: acceleration is equal to v squared over r. In order for something to stay perpetually in orbit and not ever fall, so in order for the Earth not to fall into the Sun, in order for the International Space Station not to fall on the Earth, so that the Moon doesn't fall on the Earth, so the Sun doesn't fall into the black hole at the centre of our galaxy, we need for v squared over r to be equal to gm over r squared. And provided these two accelerations balance each other out, the planets will not fall into the Sun. The Sun will not fall into the centre of the galaxy, neither will any of the other stars. The International Space Station won't fall on our heads, so long as these two accelerations are balanced. We notice we've got an r on the bottom and an r squared on the bottom, so we can actually cancel that r squared across here. And since this v is squared, if we say v is equal to the square root of gm over r, where r is the height above the centre of the body that it's being attracted to, then this velocity here, v, will be the velocity you need to maintain a stable orbit. And that is why planets do not fall into the Sun. That is why the Moon doesn't crash into the Earth. That's why the International Space Station can stay in orbit. The reason is because it's always falling, never landing, because the velocity is equal to the square root of the gravitational constant times the mass of the body that's doing the attracting, all divided by the centre to centre distance. Okay, hope that makes sense and hope that you enjoyed the video.